Big Bang has been the prevailing model for the birth of the universe for decades. However, ever since the theory was first proposed, it's been shadowed by a persistent question. Well, what came before it? This isn't to suggest that the Big Bang model is invalid. In fact, it can trace the universe's entire history over billions of years, accurately accounting for even the tiniest fractions of a second. Yet we ask, what about before that? And followed the Big Bang model back to its very first second, we arrive at a point where even cutting-edge science is left to speculate. In this sense, the Big Bang model may be considered incomplete. In search of answers, some cosmologists and particle physicists are venturing into experimental territory. Still, make no mistake, while these new hypotheses may seem far-fetched, they're being taken very seriously. Speculations now include the possibility that multiverses are real and that our universe itself might be a black hole within a separate reality. So that's confusing. Let's try and unravel it a little, shall we? But what came before? A team at the California Institute of Technology, Caltech, recently proposed that our universe may have bubbled off from a previously existing parent universe. The foundation of their study centers on addressing two of the biggest scientific mysteries in recent decades: anomalies in the cosmic microwave background, or CMB, and the paradox of the quantum singularity. Now, look, we'll delve into what the CMB is and what the quantum singularity are later on, but for now, it's really important just to note that the Caltech team used maps of the CMB created by the 1992 COBE study, as well as the more recent 2001 Wilkinson Microwave Anisotropy Probe, or WMAP. The researchers operated on the premise that these CMB maps reveal certain anomalies. In an effort to explain them, they propose that our universe may have inherited its underlying cosmic structure from this earlier parent universe. Now, exploring a cosmological hypothesis can quickly become rather confusing. The co-author of the Caltech paper, Professor Sean Carroll, helped clarify his team's early work by presenting it to the American Astronomical Society at a meeting in St. Louis, Missouri. Professor Carroll illustrated his point by using the simple examples of cracking an egg or spilling a glass of milk. He explained that each of these processes demonstrates the second law of thermodynamics, and on a smaller scale, can serve as a metaphor for the Big Bang. The key idea is that in both the case of the cracked egg and the spilled milk, disorder emerged from an original state of containment, and the arrow of time forbids this process from reversing. Nevertheless, physicists can analyze the chaos and trace it back to its origin, even without knowledge of what the original state looked like. Applying this approach to the universe, the Caltech team is suggesting that there may be evidence of an original containment vessel, implying that our cosmos could have once been housed in a structure that predated it. Alright, so now let's just pause for a moment and acknowledge the difference between a hypothesis and a theory. A hypothesis is a tentative explanation for an anomaly, while a theory is a hypothesis that has clear evidence backing it up and sustaining its ideas. In this case, the Caltech team still has plenty of work to do before they'll have enough evidence to support it being a theory. But that doesn't mean that their efforts should be dismissed prematurely. On the other hand, you might have already noticed an underlying elephant in the room with the Caltech team's work. An elephant that will actually appear throughout today's video. Namely, while the team's multiverse musings are fascinating, they still stumble when confronted with the same age-old question: but what about before that? In other words, where did the universe that gave birth to our own universe actually originate? Suggesting that there was a universe before ours is all well and good. In fact, it does technically provide a solution to the quantum singularity paradox, and it perhaps even explains some issues with the cosmic microwave background. However, at the end of the day, all we're really doing is raising more questions than we're answering. According to Professor Carroll, though, it's not simply about answering questions, but about trying to understand a much broader picture. Professor Carroll said, "We're trained to say that there was no time before the Big Bang, when we should say that we don't know where there was anything, or if there was, what it was." As unusual as the Caltech team's ideas may be, and regardless of whether they ultimately find supporting evidence, their experimental approaches offer an ideal starting point for re-examining our understanding of the Big Bang, specifically its incomplete nature. First, it is true that there are anomalies in the cosmic microwave backgrounds, or CMB, that warrant more scrutiny. but seconds, and perhaps even more importantly, cosmologists have traditionally assumed that there was just nothing before the Big Bang. If this assumption is correct, some argue it causes our most fundamental models of physics to break down in pretty disappointing ways. And that's just a discrepancy that can't be ignored. Making sense of the inexplicable. Okay, so regardless of everything else Professor Carroll said, his analogy of rewinding a cracked egg or spilled glass of milk is really pretty useful. When trying to understand how things have reached their current state, the most logical approach is to analyze the situation, gather evidence, define relevant rules, and then attempt to mentally reverse time back to the beginning of the process. Using this method, and given enough patience and some willingness to speculate, you may be able to form a reasonably accurate picture of the process's second one. To put it another way, by carefully examining a cracked egg, you can logically deduce that the egg was once wholly contained within its shell. Cosmologists and particle physicists have been attempting this exact analysis of our universe for decades, and the now widely recognized and almost universally accepted theory of the Big Bang is nothing short of remarkable. However, this does not mean that the nature of our universe has been fully explained, neatly filed away, or that we now understand every detail of its creation. There are still aspects of the Big Bang that remain unclear, and there are even some areas where the theory seems inconsistent or insufficient, depending on whom you ask. Now, one of the chief problems with the Big Bang theory is its rather troubling and physics-defying implication that at the very beginning, at some point, something must have come from nothing. This is often referred to as the quantum singularity paradox. Now, we'll get to that in just a moment. It is coming, we promise you. But before we do, let's take a moment to appreciate that thanks to the latest model of the Big Bang, we can trace our universe backwards over billions of years with a staggering degree of accuracy, all within the established laws of physics. As we do this, the story of the universe unfolds. After hundreds of thousands of years of cooling, the first atoms were fused into heavier elements in the powerful internal forges of stars. This remarkable process allowed for the creation of more complex elements, which ultimately served as the building blocks for planets, and even for the living creatures that we are today. But if we ask, what about before that? If we rewind time to before stars existed and before conditions cooled, we arrive at protons and neutrons, the fundamental particles that, when combined, form the nucleus of an atom. For context, keep in mind that protons and neutrons emerged roughly 1/10,000th of a second after the Big Bang first began, which gives a sense of the incredible timescales involved here. And we can, of course, reasonably ask, yeah, but what before that? At this point, however, we begin to enter the realm of pretty speculative physics. Now, since humanity is unable to recreate the conditions present during those earliest moments of the Big Bang, our understanding is largely based on educated guesses about what may have been happening. However, the fact that these are guesses does not mean that cosmologists and particle physicists are simply speculating without reason. Rather, they strictly follow the rules of physics, and by doing so, have identified a speculative era known as the Grand Unified Epoch. This refers to an unimaginably brief period in which a dense soup of elementary particles existed, including the now familiar quarks and antiquarks. These particles are the building blocks of protons and neutrons. When quarks and antiquarks encountered each other in the same place at the same time, they were instantly annihilated, producing a burst of energy. It was through this process that the first long-lived particles, protons and neutrons, eventually emerged, allowing the subsequent evolution of the universe. Now, naturally, we're going to ask, yeah, but what about before that? And this is where we start to encounter the truly bizarre. Taking the next step backward, we find ourselves looking at what has been called a cosmic vacuum or empty space and time. Yet according to quantum field theory, even this empty space isn't truly empty. There are still energy fluctuations occurring, causing particles to simply pop into and out of nothing. Although this may sound like nonsense to you, you might be surprised to learn that these particles have actually been observed spontaneously appearing in experiments, and their existence has actually been confirmed. The only conclusion we can draw then is that an empty space/time vacuum isn't empty at all, and that something must have come before. And, well, again, what about before that? Well, that's when we arrive at Planck epoch. Now, the period of time we're dealing with here is just 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second after the Big Bang. At this stage, what remains is something that completely defies our understanding under the laws of general relativity, the rules that govern the universe on a large cosmic scale. Instead, we find ourselves firmly within the realm of experimental quantum mechanics. Quantum gravity is still largely a mystery, with theories such as string theory and loop quantum gravity representing some of the first tentative steps toward making sense of what is, for now, almost incomprehensible. The bottom line is that if we dare to ask, what happened before that, there's simply no answer, at least not yet. Sorry about that. The idea that something came from nothing has, however, faced heavy criticism. Philosophers like David Albert have famously argued that even empty space and time are still something, and thus logically something else must have come before. He certainly has a point, but with that burning question still unanswered, cosmologists have chosen to focus their work elsewhere, basing their models on the assumption that there was simply nothing before that. Rewinding time any further, therefore, becomes as senseless as asking, well, what's north of the North Pole or something? But is adopting this mindset of something from nothing truly logical, or is it just a way to avoid addressing what we don't really understand? Asking senseless questions. Theologian and Professor St. Augustine wrestled with a dilemma similar to the modern quantum singularity question, but he did so all the way back in the 4th century. Now, he was troubled by the idea of whether there was anything at all before God created the universe. Now, eventually, Augustine found solace by reflecting on the classic biblical line, "in the beginning," and concluded that both time and the universe were created simultaneously. Now, in his view, there was absolutely nothing prior to the existence of the universe, and he believed that it made no sense to probe the question any further. Some may dismiss Augustine's approach as unscientific, yet Albert Einstein ultimately agreed with his conclusion. Einstein, widely recognized as the father of general relativity, established the now accepted principle that the presence of mass warps time. This idea can be illustrated by considering that people on a space station experience the passage of time ever so slightly slower than those on the surface of the Earth. By extension, Einstein surmised that if you wound the universe back far enough, time itself simply didn't exist, since there was also no mass. Therefore, there couldn't have been anything before, as there was no time in which a before could even exist. Einstein thus concluded that mass and time were created simultaneously, and that asking, but what about before that, is just a fruitless endeavor. Einstein's work was expanded upon in 1927 by Georges Lemaitre, a Belgian priest, cosmologist, and physicist. Lemaitre was the first to propose that the universe originated from a single, hot, dense point from which everything expanded outward, gradually forming the universe that we know today. Interestingly, it was not actually Lemaitre who coined the term the Big Bang. That name came much later, in 1949, from British astronomer Fred Hoyle. Intended as an insult, since Hoyle disagreed with the hypothesis, the term Big Bang ironically became the widely accepted name for the theory. One can only imagine how Hoyle must have felt as, over time, more and more physicists found that Lemaitre's equations held up and his terminology gained popularity. Now, just because others were beginning to agree with Lemaitre didn't mean his early model was flawless, nor did it imply that there was undeniable evidence supporting his work. That crucial evidence would only arrive much later, with the discovery of the CMB, the cosmic microwave background we talked about earlier. The identification and analysis of the CMB stands today as the most compelling proof of the Big Bang, making it one of the most significant topics in our quest to understand the universe. Interestingly, the CMB is also a key reason why some cosmologists and physicists argue that we still lack the full picture and suggest that reality might be far more complex than we can currently imagine. Most importantly, the Big Bang model itself had to be revised to account for unexpected inconsistencies in the CMB. This led to the development of the now widely accepted expansion theory, which builds upon the Big Bang and provides us with the most up-to-date model for the origin of the universe. But what is the CMB? Why did it revolutionize cosmology, and how has it led one physicist to propose that our universe might exist inside a black hole in an entirely separate universe? The perplexing mysteries of the CMB. In 1964, Arno Penzias and Robert Wilson were working with the Hondel horn antenna at Bell Telephone Laboratories. Their goal was to refine a system capable of detecting echoes reflected from balloon satellites. However, they soon encountered a bit of a persistent problem, a very faint yet unmistakable background hiss that just refused to go away no matter what they did. Now, first, they suspected a technical fault in the antenna or perhaps interference from a distant antenna somewhere else on the globe. Ultimately, though, after exhausting all of the other possibilities, they were forced to conclude, against their initial expectations, that their antenna was picking up signals from the cosmos itself. This serendipitous discovery led to the identification of the CMB, an almost perfectly uniform layer of radiation that permeates the universe. Born in the earliest moments of the Big Bang, the CMB stretches across the sky like an unimaginably immense map, offering the definitive proof that cosmologists had long sought. Only it wasn't so simple. Observations of the CMB didn't fully align with Lemaitre's model. The most significant anomaly was that the layer of radiation appeared far too uniform. In an expanding universe scenario, as stars and planets gradually formed, regions of space would have been moving apart and becoming increasingly separated. Now, this should have meant that the radiation in these distant regions would not have similar temperatures, since there could be no direct thermal exchange over such vast differences. Instead, the CMB was observed to be unusually equalized, as if the radiation had spent a long period in the same place. This unexpected uniformity contradicted everything cosmologists had logically assumed. This peculiarity was examined for years, until finally, in 1980, the revelation of inflation theory emerged. Physicist Alan Guth at the Stanford Linear Accelerator Center, later joined by Andre Linde, Andreas Albrecht, Paul Steinhardt, and others, proposed that the universe had not experienced expansion at a constant rate over billions of years. Instead, the hypothesis suggested a rapid initial expansion phase, something akin to an explosion, after which expansion continued at a much slower rate. The regions of space observable to us, therefore, display uniform CMB because they were much closer together during and immediately after this initial inflation, only drifting into the positions we see them in today. With this new perspective, inflation theory once again validated the Big Bang, though it required a significant revision of the original model. Now look, we could spend the rest of this video elaborating on CMB and how it served as a fundamental pillar of validation for the Big Bang Theory. However, the bottom line is that controversies and unanswered questions still do remain. Importantly, this is not to suggest that the Big Bang model is collapsing or should be viewed with skepticism. Rather, it opens the door for further iterations and new ideas. This is how we arrive at intriguing concepts like the multiverse or the possibility that our universe exists inside a black hole. One of the outstanding anomalies associated with the CMB is an observation regarding its heat fluctuations and patterns, specifically the apparent lopsidedness in the overall cosmic picture. When the CMB was first observed to be almost uniform in temperature, that uniformity itself posed a problem, which was later addressed by inflation theory. Since then, the 1992 COBE satellite and the 2001 Wilkinson Microwave Anisotropy Probe have analyzed the temperature variations and produced a groundbreaking map of the CMB. However, as revolutionary as this map is, it appears to show about 10% more activity on one side of the universe than the other. This may not seem like a significant issue, and indeed, many cosmologists have dismissed the observation as nothing more than a coincidence. Yet, not everyone agrees. The Caltech team that we mentioned earlier has proposed that this 10% discrepancy might be evidence that our universe inherited its structure from a previous universe. While that hypothesis may seem like a bit of a leap, the Caltech researchers are not alone in asking big questions, drawing some pretty remarkable conclusions. Indiana University physicist Nikodem Poplawski has a very similar idea, and while his hypothesis complements the Caltech team's in some ways, there are a few key differences. The most significant is that Poplawski suggests our entire universe may be nothing more than an offshoot of a black hole. We are the child of a black hole. According to Poplawski, our universe may have been born from the exit end of a black hole, otherwise known as a white hole. The input, black hole, exists in another universe, drawing in matter and energy. This material is then transported through an Einstein-Rosen bridge, commonly known as a wormhole, providing the necessary ingredients for the birth of our own universe. Now, of course, there's a lot to unpack here, and on the surface, this hypothesis might sound more like science fiction rather than science fact. However, Poplawski stands by his theory, though he acknowledges that much work remains before it can be taken to the next level. One of the biggest challenges with the idea of a universe being created by a white hole is that such a universe would, in theory, be the same size as the original black hole that birthed it. When we compare this to the assumed sizes of black holes in our own universe, we run into significant problems. Black holes are directly related to the size of the star that collapsed to create them. For example, the black hole expected to eventually form from our sun is predicted to be only a mile or two wide. Therefore, for a black hole to have created our universe, it would have had to have been unimaginably massive, large enough to have swallowed the entire parent universe. Poplawski argues, however, that the new universe wouldn't necessarily remain its original size, but could expand over time as more particles and matter are added. This hypothesis actually connects to the Big Bang Theory and, by extension, also addresses the discrepancies observed in the cosmic microwave background. On the other hand, what about the additional issue that black holes are thought to lose mass over time, as famously theorized by Hawking, who introduced the concept of Hawking radiation? Well, according to this theory, black holes eventually fizzle out. In the context of Poplawski's hypothesis, this suggests that our universe also will eventually have to disappear. However, Poplawski offers an explanation for this as well. He suggests that the universe birthed from the black hole does not vanish. Instead, the black hole itself simply fades away, disconnecting from the universe it created and causing the wormhole to close. Poplawski adds that in the case of our universe, the black hole is already closed. This explains why we don't observe any clear signs of a constant flow of new matter and energy being fed into the cosmos. When considered together, the hypothesis not only addresses the CMB problem, but also helps answer another long-standing mystery about the universe. This secondary mystery concerns the shape of our universe, whether it is open, closed, or flat, each of which represents a different model that can be applied to the Big Bang. Understanding the specifics of each version involves a whole complicated set of theories, but in short, if our universe were flat or open, you could never reach its end because space would continue on indefinitely. A closed universe, as suggested by Poplawski's hypothesis, allows you to reach its end, but doing so would simply mean cycling back to your starting point, much like walking around the surface of a planet. Now, of course, there's no evidence to confirm or disprove any of these theories. However, it would seem logical for our universe to be closed if it was indeed born from a black hole. What's particularly intriguing here is that if our universe is closed, it might be possible to test and conclusively prove this by detecting light from stars on one side of the universe appearing on the opposite side. For Poplawski, the question of whether the universe is flat, open, or closed isn't his main focus. His primary goal is to provide an answer to the age-old "what about before that" question. Interestingly, black holes themselves contain a similar quantum singularity paradox. It remains a mystery what happens at the center where existing laws of physics seem to break down. As Poplawski explained, "In my model, when the universe is born, there is no problem of an initial singularity. Instead of being infinitely small, it has the radius of its parent black hole. Rather than black holes ending in singularities, this model suggests that they give rise to universes." End quote. At this point, you've probably noticed the obvious looming issue that threatens to undermine everything Poplawski is proposing. I will address that shortly. But even before we get to that question, it's important to recognize that there are several other significant problems with Poplawski's ideas. The most notable among them is that black holes themselves are still highly speculative, and in particular, wormholes remain little more than science fiction. Now, in the original Einstein-Rosen bridge equations, a hypothetical wormhole closes the very instant it opens, famously requiring an additional exotic material for a wormhole to ever remain open and stable. In this context, Exotic material refers to a completely hypothetical particle with negative energy density, a substance with such bizarre properties that it would move in the opposite direction when pushed. Now, although entirely theoretical, exotic material is necessary for a black hole to lead into a wormhole and, by extension, for there to be any possibility of an entirely separate universe existing on the other side. Now, setting that aside and returning to the "but what about before that" question, we must once again acknowledge that these conjectures raise more questions than they answer. It's disappointing, we know. When confronted with this reality, Poplawski candidly remarked, "So, was that universe born from a black hole in another universe, and so on? It's a problem of an infinite number of universes." That's a very reasonable criticism. Is it even worth asking? Now, at this point, you might be wondering about the purpose of these hypotheses. Perhaps you're arriving at the same conclusion as St. Augustine or Einstein and thinking, well, why? Why even ask? Why not just draw a line and adopt the mindset of most physicists and just work under the assumption that there wasn't a before that's even worth considering? Now, it's important to remember that working on a hypothesis isn't always about proving a new concept. Often it's simply about examining a dilemma from a different perspective, no matter how unusual that angle might seem. By exploring these unconventional viewpoints, new information may come to light. Even if this information doesn't validate the original hypothesis, it can still contribute valuable insights to other, entirely separate hypotheses. Understanding the universe is a collaborative endeavor, and scientific progress thrives when radically different perspectives come together to build a more complete and cohesive picture. On that note, there are far more unanswered questions and paradoxes than we had time to discuss today, including one of the strangest of all, the now widely accepted existence of dark matter and dark energy. We didn't have a chance to explore these mysterious substances or to delve into how they relate to the Big Bang today, but current estimates suggest that dark matter accounts for about 85% of all mass in the universe, while dark matter and dark energy together comprise about 95% of total mass and energy. Ordinary matter, that's the stuff that we interact with, that makes up only about 5%, highlighting just how little we truly understand about the universe's fundamental nature. Perhaps most astonishingly, scientists now theorize that dark energy was the primary driving force behind the Big Bang itself, despite the fact that this enigmatic substance does not interact with light and seems, in many ways, to exist on an entirely different plane of reality. The point is that we have almost no understanding of what dark matter is, how it works, or where it came from. This makes it abundantly clear that our model of the Big Bang does need further refinement. And really, would it be so surprising if the answer to what dark substances are ended up being discovered by someone trying to prove that our universe is actually a black hole offshoot from another universe? I mean, maybe. Thanks for watching.